Now David wants to solve the equation for 1000x minus 800 equals 1600. What easier equation could he solve instead that would give him the same solution? In other words, what equivalent equation has easier numbers to work with? Well, as you look at this, you can clearly see that each of these numbers, 4,000, 8,000, 16,000, all of them can be divided by 1,000. So probably I would say for A, look, I'm going to divide there's two sides of the equation, and there's two terms on the left-hand side and one term on the right-hand side. In order to simplify this, I'm going to divide every single term by 1,000. So this equation becomes 4x minus 8 equals 16. Much simpler to deal with. It says justify your equation in part A. Justify that your equation in part A is equivalent to this by showing that they have the same solution. Okay, on the simpler one, if I add 8 to both sides of this, I'm going to get the 4x equals 16 plus 8 would be 24. And if I divide both sides by 4, I get that x is the number 6. Now I got to deal with the beast, right? With the beast, I'm going to add 8,000 to both sides. I get that 4,000x equals 24,000. And I'm going to now divide both sides by 4,000. So x equals 24,000 divided by 4,000. And when you look at that, there's a giant 1 there. Right? Certainly I've got 24 times 1,000 over 4 times 1,000. And I can go further, right? 24 is 6 times 4. So I could say, hey, this is even simpler. This is 6 times 4 times 1,000 over 4 times 1,000. So I have a huge value of 1. And when I divide that, when I eliminate or realize that that's just the number 1, I end up getting that this is 6. Much simpler to deal with. David's last equation to solve is x over 100 plus 3 over 100 equals 8 over 100. Write and solve an equivalent equation that is easier that would give him the same answer. I would say clearly what I would do is I would multiply both sides of that equation by the number 100. So consider if I've got 100 over x plus 3 over 100 equals 8 over 100. And I magically multiply both sides of this equation by the number 100 over 1. 100 over 1. On the left-hand side, as I use the distributive property, I get 100x over 100 plus 3 times 100 over 100. And I immediately see there's a giant 1 there, right? That's x plus a giant 1, 3. And then that equals, on the other side, 8 times 100 over 100. Again, that's the number 1, so I'm left with 8. All I need to do is subtract 3 from both sides, and I see that x is the number 5. X equals 5. 5 100ths plus 3 100ths equals 8 100ths. Oh yeah, that's true. Examine the triangle, it's a rectangle at right. If the perimeter is 120, which equation below represents this fact? Once you've selected the appropriate equation, solve for x. The perimeter. Well, the perimeter is the distance all the way around it, and I've got two different distinct values here, right? One of them looks exactly like this, 6x plus 11, and there are two sides that have that length, and then there are two sides that have the length 2x plus 5. So if I think about that, I could write it in maybe a little bit a nice compact form. I could say I've got two of these 6x minus 1s, and I've got two of these sides that are 2x plus 5s. And when I add those up, I get a total of 120. The perimeter is 120. Which one of these equations do I have? Well, this one's just half the perimeter, right? That's not the entire perimeter. This would be great if it was a square and all four sides were 6x minus 1. Oh, and this one right here, this is, if I multiply that, that would give me the area, right? Length times width would give me the area. So what I have here is C. C is the equation. And now if I use if I solve this, let's see, I guess I can write 120 equals 12x minus 2 plus 4x plus 10. Yeah? If I combine those, that's 16x, and then I've got a plus 8, and over here that's equal to 120. I'll subtract, oh, why did I write, it's 120, not 12, 120. If I subtract 8 from both sides, I get, is that 112? Yeah, equals 16x. And then finally on both sides, we're going to divide by 16. On the right-hand side, I end up with just x when I divide by 16. That's why I selected 16. On the right side, I get, left side rather, I get 112 divided by 16, which I'm told is the same as the number 7. So x is 7. Which of the following expressions is equivalent to 12 times x raised to the 6th power? So let's take a look at A first. In question A, I've got 3 out by itself, and what I have next is, and I'll place this in, I've got 2 factors of 2x cubed. So there's one of them, and then another set of 2x cubed factors, right? That 2x cubed was raised to the 2nd power, so I have 2 of those identical clones that are factors. Again, factors, things that are being multiplied together. So if I look at this, I can see that I've got a 3, a 2, and another 2. Well, 3 times 2 is 6, times 2 is 12. So if I bring those factors together and write them as a single number, I've got 12, and then I have an x cubed times another x cubed. Well, 3 factors of x and 3 more factors of x, that's 6 factors of x. That's 12 times x, x, 6 factors of x, or 12 times x to the 6th power. So this is clearly, right, the same as our target. This is 12x squared. So expression A is definitely another way that you can write 12x squared. For expression B, I have, let's see, okay, well, this is a little different. I've got 6 x to the 8th power, and I'm multiplying that by 2 terms. One of my terms is 2x, and the other term is a 2. And this is not always necessary, but I'm going to do a generic area model here to help me organize my work. So one of my factors is 6 times x to the 8th, and the other one is 2x, and the other one is minus 2. So when I multiply 6 times x to the 8th, I get 2 times 6, which is 12x to the 9th power, right? 8 factors of x, and one more is 9 factors of x. And then I've got a negative 12x to the 8th power. Now, unfortunately, these are not like terms, right? They're different. One's got 9 factors of x, and the other one has 8 factors of x. So I cannot combine those. So the best I can do is just write this as 12 times x to the 9th power minus 12 times x to the 8th power. And this is not equivalent to 12x squared. And it's okay, there's no reason to be sad about it, but that's just the facts. Let's take a look at C. For C, I've got 144 x. This is quite interesting that this is here, x to the 12th, and raised to the 1/2 power. Now that's really, really interesting. That would be here so soon, and I'm not exactly sure how I'm gonna, approach this, but let's take a look at a couple examples. So if I had, let's say 5x to the 3rd power, and I raise that to the 2nd power, that becomes 5 to the 2nd times x to the 3 times 2, or 6th power, right? This would be, I'd write it out twice. If I wrote this out twice, it would be 5x cubed, 5x cubed. Well, you can see I've got 5 and 5, so that's 5 to the second power. Then I've got 1, 2, 3 factors of x, 1, 2, 3 factors of x, that's x to the 6th power. So when I raise 5x cubed to the second power, this is what I get. Now, what if I was to take 5 to the second times x to the 6th and raise that to the 1/2 power? Well, before, you'll notice what I was doing, the shortcut was I was multiplying this 2 times 1 to get 5 to the second, and 2 times 3 to get 5 to the third. Well, what if I multiply this, right? I could get 1/2 times 2 would be 1, and 1/2 times 6 would be 3. So if you look at this, this brings this right back to where it started. It brings it to 5x raised to the third power. So there's something about taking a number like 3 and squaring it, and then taking that result, which is and then taking that and raising that to the 1/2 power, right? You end up getting just the number 3. If you square something and then you raise it to the 1/2 power, you get back at 3. Well, it turns out that that's pretty much what the square root function does as well, right? If I take the number 3 and I square it, and then I take the square root of it, I end up getting the number 3. Anyways, let's not belabor this too much because we'll be much more formal about it later. But right now, I just want to rewrite this as 144 to the 1/2 power times x to the 6th power. And we could leave it there, and that's nice, but I would encourage you to take a look at what 144 to the 1/2 power is on your calculator. And it might be kind of an interesting observation to make. If you've got a TI-84 or 83, it would look like 144, and you'd hit this symbol, and then I would use parentheses and go 1 divided by 2. And then consider writing that value in right here instead. And I look forward to seeing your answers for that. Last question is D. On D, we have 60x to the 10th power and then a y over 5x to the 4th power over y. Well, one of the things I spot right away is there's a giant 1 there, so I don't need to lug these y's around. Another thing I see is 60 divided by 5, I believe is 12. Is it? 5 times 12, 10, yeah, it's 60. So I could say I've got 12 times 5 over a 5. That's 60 over 5. And then for those x's, I'm going to write it as times x to the 4th, x to the 6th. And this isn't entirely necessary, but I'm doing this just to illustrate that in my denominator I had an x to the 4th. So when I write it this way, I can see that there's definitely a giant 1, another giant 1, in the form of 5x to the 4th over 5x to the 4th. So if I take a look at what's left behind, I just have only 12 and x to the 6th power, which is what we wanted. So this is also. This was also. This one might be, I don't know, maybe it is. It really all depends on what 144 raised to the 1/2 power is. So you might want to look at that and decide if C is the same form or not. 117 says multiply each of the following expressions and please show all your work. I'm going to use a generic area model for each of these problems. So for A, I can see it's a binomial times a binomial. So I'm creating a 2x2 grid. And across the top, I'm going to go ahead and place an x and a +3, and then a 4x and a +5. And now as I fill in each of the parts that make up the area of these individual rectangles, the first one I'm going to fill in is this is 4 times x to the 2nd power. That's a 4x times an x. The next one I'll fill in is this is 12x, that's 3 times 4x. And this will be 5x, that's 5 times the x above. And then finally I'd write 5 times 3, which is 15. Now, two of those are like terms, right? So for A, my final answer, I would write as 4x squared plus 5x plus 12x is 17x, and then plus the number 15. So this is the simplified version of that product. For B, I have a binomial times another binomial, so another 2 by 2 grid. And across the top here, I've got a negative 2x squared and a negative 4x. Very important to have those sides, for sure. And then I've got a 3x and then a 4. So as I fill in the parts here, the first box I'm going to fill in is 6x to the, negative 6x to the third power. So that's a negative 2 times positive 3. There's the negative 6. And x squared times x is x to the third. And then I'm going to have a negative 12x to the second power. Before I had x to the third, now x to the second power. In the box below on the left, I'm going to have a 4 times negative 2x squared, which would be negative 8x squared. And then my final box is 4 times negative 4x, which would be negative 16x. So my final product then, when I go ahead and combine up the like terms, I've got a negative 6x cubed, and I can combine my x squared terms. I have a negative 12x squared and a negative 8x squared, which when combined is negative 20x squared. And then finally, I've got a minus 16x. So that is precisely the product for B. For C, another binomial. So, and you know what, C I'm going to write way over here. There's enough room for it. So on C, I'm going to go with another 2 by 2 grid. I've got a 3y and a negative 8. I've got a negative x and a positive y. As I multiply 3y times negative x, it's 3. Well, actually, that's not true. It should be negative 3xy. And you could write negative 3yx too. That doesn't matter. I tend to write x first. When I multiply negative x times 8, that would be a positive 8x. Below on the left, I've got 3y times y, which is 3y squared. And then on the bottom right, I've got a negative 8 times y, which is a negative 8y. And then when I combine all those terms up, I end up with, I guess I would put the 3y squared first, and then a minus 3xy, and then a minus 8y, and then the last thing I have here is a minus 8x. So those are precisely the parts that I get from my factor. The last one, I don't quite have enough room on the screen, so let me clear this to do the last problem. On it, we're going to multiply, well, it is a binomial times a trinomial, so I'm going to do 3 columns, 1, 2, 3, and I'll do 2 rows. For my columns, I'm going to place a 3x, a 5y, and a negative 2. And for my columns, I'll place y and negative 4. So going across the top, I have a 3x times y, which I would write as 3xy. And then I have a 5y times y, which is 5y squared. And then finally, I would have negative 2y. Going along the bottom row, 3x times negative 4 is negative 12x. 5y times 4 is negative 20y. And negative 4 and negative 2, that's a product of 8. So lots of things here. I do have some like terms actually. The negative 20y and the positive 2y are like terms. And actually those are the only two that I have that are like terms. So I can combine those, but everything else has to stay alone. So let's see, I'm going to begin by writing this as 5y squared. And then I'll do plus 3xy, and then I guess I'll do minus 2y, and then minus 12x. Oh, you know what? It's silly that I'm sorry. I said minus 2y, but I didn't mean that, because I need to combine those like terms. So I'm going to do minus 22y, That's what I'm writing, minus 22y. And then I will have a minus 12x, and then finally plus 8. And if I look at this, I'm like, did I miss anything? There's 1, 2, 3, 4, and then these are together, so 5. There should be 5 terms. I have 1, 2, 3, 4, 5 terms, and I think I got everything. So this should be the product of this binomial times this trinomial, something with 2 terms times something with 3 terms.
So I decided to record this video with actually a piece of paper and a real pen. I look at every single time I see these transformations happen in your homework, and they kind of look like approximation sketches of kind of what it might look like. And you really need to get to where you're actually plotting these points accurately and reading information from that graph. So if you look at these 4 shapes, I've sketched these, right? This was, what question is this? Well, you know what question is. It's 318. And basically, I sketched these. They're actually not sketches. What I'm doing is I'm looking at kind of the internal structure of the points to figure out where they go. So one of the things I noticed was that, you know, it's 2 that were horizontal and then 1, 2, 3, 4 that were vertical. So I got that exactly. And then there was just 1 that went up. And if you look at this next bit of it, it goes down 1 and then over 3, right? And I could see that in the diagram in the book, but I could easily emulate that here on the paper. So just down 1 and then over a total of 3. And then it was like up 3 and back 1. In fact, look at that. Down 1 over 3, up 3, back 1. That's a right angle right there. And I know that's a right angle because these slope patterns, up 1 over 3, is the opposite reciprocal of down 3 over 1. This is a slope of negative 3. This is a slope of positive 1/3. And then I think it was up. Up 1 and then over 1, 2, 3, 4, 5, 6. So up 1 over 6. Anyways, when I have that, it's a very accurate sketch of exactly what this looks like. And what I do now, the first thing they ask us to do is a reflection across that line, the line that was just one unit directly below it. In order to do that reflection, I've got, let me use this little green pen. I'll just put dots here. I have a point that's here, right? This point is, that's terrible. This point is equidistant from this point, so 1 unit, 1 unit. And then from here, I need to go 1, 2, 3, 4 more units away. 1, 2, 3, 4 more away. So that's the next point. And then this point is obviously right there, and then there. And then you can see this one is just 1 away there. And then I'm going to go from here 1, 2, 3, and over 1. And 1, 2, 3, 4. 1, 2, 3. Oh, this is this point there. So I can see all of my points, and now you just grab a ruler and connect them, right? So I'll connect these points, and then I'll connect these points, and then let's connect this. This, and then 2 more segments, this segment and this segment. Now when I'm done, it should be, you know, a very compelling, very convincing reflection across that line, and you can see absolute symmetry there. And in fact, you know, some of the properties is that if you've got a line of symmetry that this segment here is equal to this segment. If I draw all the lines that are connecting these, all of these lines would be parallel to each other that connect. If you've got lines that are connecting this is the original point and this is the image of it. If you connect all of those, all these lines should be parallel lines. And these parallel lines are perpendicular to the axis of symmetry, or the line of symmetry too. So this is what I'm looking for, and I think this accuracy, this level of, you know, a little bit more precision is kind of called for, particularly when we're doing problems that involve the Cartesian coordinate plane and we're trying to read coordinates off of it. There's one more thing I want to look at, and that's when we have to do a rotation. So if you look at this shape and compare it to the one in your book, one of the things I noticed was I started with this point in my mind, and my point of rotation was over to, up to. So if you look at what was in the book, this is exactly the relationship that was there. To go to this corner, it was down to, back to. This one, it was up 4 and back 1. And then these were parallel to each other. I could see they had the same slope pattern of, this was, you know, this is up to, over to, up to, over to. So these lines were the same. And then these lines are parallel also. Anyways, what they're asking us to do is to do a rotation about point P. And the rotation that they asked us to do was 90 degrees counterclockwise. Well, to do that, I'm going to place a piece of patty paper over it. And I don't need to use the whole piece of it. I can use this for many other problems. But this is something that I encourage you to have a piece of it in your just in your notebook so you can grab it when you need it. But if I kind of just quickly put points where these are at, right? So I've got those vertices right on there. The other thing that I'm going to do is I'm going to add this little line that's kind of lined up with the horizontal line below it. So what that's going to allow me to do is know when I've reached the 90 degrees. So I'm going to put my pencil right over that point of rotation, and then I'm just going to go counterclockwise, which is that was clockwise, so I want to go counterclockwise, and I want to do it for a full 90 degrees. And right there I'm at 90 degrees when that's lined up there again. And it's a little difficult, but I can see where these points are, right? And I might do this thing where I take this point and like maybe try and grab it and see it underneath the, it's kind of actually difficult to transfer over, but I can see that point. Another thing that you can do is if you take your patty paper and flip it over and you just put dots, you kind of darken these individual dots, so just kind of ink that, put some dot there. Okay, then when you get it lined back up in the right place, let's see, rotate and 90 degrees. Once it's in the right spot, if you now kind of, let me bring this back up here. If you now kind of just trace over this a little bit, the lead that you have on the other side of the patty paper will kind of transfer to these points. And when you move it over now, you can see a very faint image of where this triangle went. So this is exactly what I get when I do a rotation of 90 degrees about the origin. I should connect the dots for that. And then the other thing that that we've been doing is we've been reading some of these coordinates and looking at some of the relationships with them. Now, without patty paper, could I do that? Probably. What would that look like? I'm not sure. But right now, I definitely have an image where I can think about, how do I do a rotation like this? So, for example, I know that this point goes to this point. In fact, I'll mark them both green. So they go to each other. Well, how do I know, where a point like this is going to go if I rotate 90 degrees? Well, look at this. I can draw a line from my center of rotation to that point. And when I rotate 90 degrees, notice that this line right here, right, is forming a right angle with my center of rotation and the destination. And look at this. This was up to, back to, or up to, over to. If I go back to and up to, I'm at the right spot. And you can find patterns like that for each of these points, right? This from P to here was back 3 up 2. Well, if I go up 3 and over 2, you can see that's exactly where that went. For this point, it's over 1, 2, 3, 4, 5, and not up or down at all. Well, from here I just go up 1, 2, 3, 4, and 5.
At an aunt's wedding, Nicholas collected data about an ice sculpture that was about to completely melt. The thing's just vanishing. So in case you're wondering, this is like an ice sculpture of a lovely, I don't know, swan or something. And Nicholas, I don't know how tall it was originally, but when Nicholas starts watching his, it's at a height of a 10, well, it's at 10 inches by the time he sees it. And it's, you know, you can see what's happening. As time increases, the height of the sculpture is decreasing. Well, it's the question A asks us to write an equation for the line of best fit. And I don't know exactly where, you know, the best fitting line is, but it's somewhere certainly in this region, right? There's a line that, you know, kind of is some, you can see quite a few of the points are exactly on that line. Some are above, some are below. But in general, that's a line that's, you know, attempting to state what's happening overall with this pattern. And a couple things we can notice about this line, right? One of them is up here, we've got a y-intercept at 10. So we could say for our parameter, b is 10, right? And that corresponds to the y-intercept. Another thing that we can see is there's pretty clearly a rise and a run here. And you can see as time is increasing, the height of the sculpture decreases. And there's a lot of little places where I could draw, you know, a sloped triangle, but it might be difficult to read the actual data points. What I'm looking at is, you know, the big picture. I think this would be probably the easiest. Is if I just look at this, I've got a rise of -10, right? It went down by 10, and it went down by 10 in a run of 4 hours, right? 1, 2, 3, 4. So if I just look at this massive slope triangle, I've got two things that I can see here, right? I've got a change in y of -10, and I've got a change in x of, what is it? It's increasing by 4. So x is increasing by 4, y is increasing by, y is decreasing by 10, and x is increasing by 4. So I could reduce that slope, right? And let's write that as our other parameter. Our slope m is -10 fourths, which is equivalent to -5 halves. So overall, it's going down it's going down 5 inches for every 2 hours. So down 5 over 2. So with that, because we have our two parameters, we could clearly write the equation of our line, right? Our line is y equals -5 halves, right? It shrinks 5 inches every 2 hours times x, and then plus 10. So this is an equation of probably a pretty reasonable line of best fit. And then it says next, based on your equation, how tall was the ice sculpture 1 hour before Nicholas started measuring? So if you imagine right here, he started measuring at hour 0, and they're asking if I go back an equal distance, like in here, right, at -1, about how tall up would the ice sculpture have been? Well, what you could do is that you could just literally feed -1 in as input into this function, right? If x is -1, and then just see what it says y is. So y would be -5 halves times a -1 and then plus 10, and which would make this +5 halves. And +5 halves, by the way, is a 2.5. So this looks like about 12.5 inches. So, you know, probably 1 hour before he started measuring, the sculpture was, you know, perhaps 12.5 inches tall. There could be other variables at play. We don't know everything that happened, but this seems like a pretty reasonable assumption. I could certainly make arguments for why it would have been taller or shorter, and I think thinking about those things and really kind of being able to make those arguments is what's more important, right? Is kind of your thinking and your reasoning skills, but certainly having good mechanics and understanding how to, you know, approximate a line of best fit, and definitely how to write the equation of a line with the proper parameters. That's the skill that we're working on.